selected a topic for a presentation and you plan to give a presentation, then talk to me today, by the way. So we talked about generalized entropy last time. And we're going to conclude that discussion with a derivation of the generalized entropy for a stationary black hole. So what do I mean by a derivation? What I mean is that S of rho, that is the von Neumann entropy in quantum gravity, for a stationary black hole is equal to the generalized entropy, which we defined last time as a quarter of the area plus S rho Q of T. So the gravitational area term plus the entropy of the quantum fields outside the black hole. Okay, so we're going to derive this from the replica method. Trace of rho to the n is e to the minus beta h times n, because remember we found we thought of the Euclidean black hole as a saddle point that comes from calculating trace of rho e to the minus beta h. So this is what we're going to calculate. Let me remind you of the case n equals 1, where you just are calculating the partition function of the black hole. So in that case, we had this trace e to the minus beta h was the path integral with this boundary condition. Okay, so what I mean by that is that far away from anything near infinity, there should be a circle of size beta, and then it's up to gravity what to do everywhere else. And that's the Euclidean time circle, TE is TE plus beta. And we said in the semi-classical approximation, you can calculate this path integral by the saddle point, and the saddle point is the Euclidean black hole. Saddle is the Euclidean black hole. So the path integral is approximately e to the minus s Euclidean of the black hole, and then there are some quantum corrections coming from, say, loops of the quantum fields on this background. For the rest of this discussion, I'm going to ignore the quantum effects, and I'll put them back in at the end. Now we'll go to the case of n not equal to 1. Z of n, the replica partition function, is trace of e to the minus beta hn. And in the replica method, recall that the von Neumann entropy is minus n dn log z of n over z of 1 to the n, evaluated at n equals 1, which we can also write as minus n dn of log z of n minus n log z of 1. By the way, let me step back a minute. So I'm using this replica method to derive, so we just want to derive the entropy of a stationary black hole. There's an easier way of deriving this. We could just calculate the path integral and get the entropy using thermodynamic relations. Like if we had the path integral as a function of beta, we could just do 1 minus beta d beta log z. The reason I'm using the replica method instead is because the method that I'm describing here is going to generalize to other situations. So in fact, the derivation that I'm giving, we're talking about the stationary black hole, but this is also going to give us the Rutakanagi formula, the island formula, all the other entropy formulas that we're going to talk about for the next couple lectures. Okay, so this thing in brackets here, so this is the action of a Euclidean black hole with at temperature n beta, right? Because z of n is just multiplying the temperature by a factor of n. So we just take that thermal circle and make it a factor of n times bigger. And then the other term here is n times the action with a circle of size beta. This second term, I'm going to think of in a funny way. Okay? So instead of thinking of this as n times the action, I'm going to think of this as, I'm just going to take this thermal circle here, and I'm going to multiply it by n, but I'm going to do it without changing the metric. Okay, so I'm going to think of this as being the action for a metric which is the metric at temperature beta, but where I've artificially decided that the coordinate has period n beta. And when you do that, you get a conical defect, because I didn't change the metric. Okay, so this point is a conical excess. This is just a trick, okay? But so the point is that it's the difference of two terms. In one term, we change the size of the thermal circle, but then we allow gravity to back react. And when gravity solves the equation of motion, it doesn't allow singularities in Euclidean. So you get a nice smooth geometry if you calculate the Euclidean black hole at temperature n beta. But over here, we just have n copies. We're just taking an n-fold cover of the original black hole, and that produces a conical excess. When we calculate the action of this red one, we should just ignore the conical excess. Okay, because this was just a trick anyway. There's not really a conical excess. We really just mean n copies here. So when we calculate this action of the cone, we shouldn't include any kind of delta function or anything funny at that point, because it was just a trick. Okay, so I'm going to put like a prime there that means ignore any delta functions at the tip of the cone. Okay? So now, do you need a regulator for that? No, you just literally ignore it. So you plug your metric into the action, and you don't put a delta function there, and then you'll get the right answer. But we're about to introduce a regulator. So what we're going to do, let's see, these are e to the minus Euclidean actions, so let me put a minus sign here and a plus sign here, where those are the actions. Those pictures represent the action. Now I'm going to set n is 1 plus epsilon, or small epsilon, because that's all we're going to care about for calculating the entropy. And I'm going to write this as the following 4 terms. Okay, so the first term is just the same, is just the black hole at a different temperature. It's the same as this term here. G now means the original metric. So the slightly hotter or colder black hole has a slightly different metric, so there's a delta G, and the temperature is a little different. Now I'm going to add to this a regulated cone. I'll come back to explain this in a minute. And then I'll subtract that same thing. Let me come back to that one. And then we have that last term there that's unchanged from before. So that last term has thermal circle 1 plus epsilon beta, but it's the original metric G. Okay, so what are these other geometries? They both have the same circle of size 1 plus epsilon beta. Away from the tip, they have metric G. But I've just smoothed out the tip however I please. I've just cut out the pointy tip of this metric and replaced it by something smooth. This is a solution of the first term is a solution of the equations of motion. That was the black hole at a different temperature. This is a solution of the equations of motion. It's a black hole at the original temperature. But this new thing I'm adding and subtracting is an off-shell solution. Sorry, it's an off-shell geometry, I should say. It's not a solution of anything. It's just something else. But the reason it's useful is because these two terms cancel. The reason for that is that this one was a solution of the equations of motion, and the action is stationary at a solution of the equation of motion, including for off-shell variations, of course. Okay, so this does nothing to the action. So these two terms cancel, and that means that we're now doing just this calculation, and you can see that any contribution to the action in this calculation is now localized at the tip. It's localized at the pointy spot. We're hoping to end up getting the area for this calculation. It's the area of the black hole, so it's localized at the tip. So we've now reduced the calculation to a calculation at the tip. Yes?
I didn't understand the argument.
So what I mean by these are Euclidean actions, and the variation of the Euclidean action is 0 when you vary around a solution. This one is a solution, and that's a variation of it. So they have the same action. Other questions?
How is the second term defined? Should I impose a boundary condition?
Sorry, this one you mean?
Yeah.
I just I just integrate root GR on this metric. It's the integral of the Einstein action over this manifold.
I see. So what is, let's see.
We're about to calculate the contribution at the tip, so maybe that'll help, but.
With the boundary term?
You mean the GHY term here?
At
The other side, yeah.
There's no boundary term here, no. There's a usual boundary term at infinity, but there's nothing extra here. It's just the Einstein action.
Is it a solution to the Einstein equation?
No. But you're allowed to calculate its action.
Wait, so you're saying that delta SE equals 0 because the second guy is just the variation on the first guy?
Yes, it equals 0 because the first one is a solution.
And the contribution from the tip and the second one is infinitesimal? Because I agree that the second one is a variation of the first one except at the tip.
It's gonna be everything's gonna be order epsilon, including the contribution to the action that we get from the tip here. You're worried about the fact that it might be an infinite variation. No, we're gonna calculate it, it's order epsilon. Okay, so we've reduced this problem to calculating the Euclidean action, which is 1 minus 1 over 16 pi g integral root gr for the pointy tip. Okay, this little cone is just supposed to mean this part of that metric, plus 1 over 16 pi g times integral root gr for the rounded tip, which is the off-shell solution that we're using to regulate. First one is 0. Because, well, we said a few minutes ago that we're not including any kind of delta function from the pointy part. Okay, so there's really a prime here, like don't include any delta function from the pointy part. And that means this is just a smooth metric being integrated over an infinitesimal region, and therefore it's 0. Because we could take the region to be very tiny. Great, just this term. This is the answer, this term.
Isn't that also over an infinitesimal region?
Yes, but it's very curvy. Because we need this part, this part here has, if you're sitting at this part, you think that you're about to hit a conical defect with deficit 2 pi n. But it must curve very quickly to smooth that out. In other words, in this one, we've declared that we're not including the contribution of the curvature at the tip. But in this one, we are including the curvature at the tip. So the final answer is just going to be the contribution of the curvature at the tip.
No. So if that's a finite contribution, then why didn't we have to worry about it in the first term? Like in the one with the purple bounce around it?
It's finite as we take this distance to 0, which is the regulator, but it's order epsilon, like n minus 1. So it's a small. So we're about to write that term.
But since you're just cutting off that cone, shouldn't you add a boundary term?
No, it's not that we're cutting anything off. It's that these two parts cancel, and so we're just left with the contribution of the Einstein piece here.
Now, delta G is also order epsilon. And
That's right.
And the statement that the action is stationary there is the statement that the variation in the action as you vary g by order epsilon is like order epsilon squared. But then don't we get an order epsilon contribution from that tip? And so that would like contradict it.
Okay, let me write the formula and then we can come back to that question. Okay, so this is the action, the Einstein action of the smoothed tip. I claim that this is 4 pi over 16 pi g times 1 minus n, that is, wait, 1 minus n? Yeah. So that's order epsilon. Now, in all these calculations, I've suppressed a bunch of extra directions. Okay, I'm only drawing 2 dimensions, but we're in d dimensions. So it's times area in the transverse directions. So I'm going to explain how this calculation is done in a second, but let's come back to your question. What was the question?
So the statement that the action is stationary means that the variation in the action should be order epsilon squared.
Yes, that's true for the difference between these two.
Right.
Yes.
But then you're saying that the contribution from the tip is order epsilon, not order epsilon squared.
Yes. But this has contributions everywhere, not just at the tip. And the contribution of delta G in this piece of the geometry is going to cancel the order epsilon piece that came from the tip over here. Well, sorry. Both of these have contributions everywhere. It was only in the second line that we canceled off the non-tip, because these both had metric G away from the tip. On the first line, they both have contributions everywhere.
Well, the argument that they cancel is based on the fact that like the second one is a small variation. The first one, small meaning
Yes.
like order epsilon.
It's small, but it's everywhere. It's not localized at the tip.
But it's not a small variation at the tip, right? Because you don't have metric G at the tip.
No, it's small. It is small at the tip. It's G plus delta G.
I thought you only had metric G on the right figure away from the tip.
The difference between pointy and curved is also order epsilon.
Oh, okay.
So this last part of the calculation, the contribution of the curvature at the tip, this is a theorem. So this is the Gauss-Bonnet theorem. Do I want to go through this? I don't know. Do you want me to go through it? To do this calculation? Okay, I'll do it. Okay, so Gauss-Bonnet says that the integral over a 2-manifold of root GR is 4 pi times the Euler character, which is a topological invariant of the manifold, minus the integral ds of the extrinsic, trace of the extrinsic curvature k over the boundary. We don't have to use Gauss-Bonnet. We could just write down a metric that regulates the cone, and then just do the integral. But I'm being fancy and using Gauss-Bonnet. So the Euler character of a disk is 1. This term is well, the extrinsic curvature of a circle is 2 over the radius. I'll leave that as an exercise. That's a 2-line calculation. And then, so this term is 2 pi n r times 2 over r. 2 pi n r being the circumference of the circle when we have size 2 pi. So we got 4 pi times 1 minus n, which is what I claimed. Okay, so putting it all together, we can now go back to our replica trick, which says that the von Neumann entropy is minus n dn of the calculation we just did, which gave 1/4 of the area times 1 minus n. And therefore S is 1/4 of the area, and that's the classical entropy as claimed. Questions?
Where's the minus epsilon supposed to be?
Sorry? N was 1 plus epsilon.
Oh, okay.
Yeah.
So you're saying that the metric is only order epsilon away from G
Yeah.
at the tip.
Yep.
But you also said it has to be very curvy. But I guess that doesn't.
Yeah, it's epsilon times infinity is what you're worried about. That's true. There's some funny order of limits that's required in order to make sense of that epsilon times infinity at the tip. Actually, for this calculation, you can do that order of limits any way you please, and you'll get there's only one answer that you can get. But more generally, that order of limits actually matters. And so like if you have gravity with higher curvature corrections, there's some issues with doing this calculation that has to do with that order of limits. I'm actually not sure what the status of that is. People were talking about it for a couple of years and I lost track. I'm going to be very brief about the quantum corrections. And the reason for this is that I tried to put together like a coherent explanation of the quantum corrections that would fit into a lecture, and I failed. It's just really subtle and complicated. And it's spread over many papers with no simple derivation that I dare to do in lecture. So I'm just going to kind of say roughly how it works, and we'll have to be happy with that. So roughly, the point is that when all these path integrals that we're doing are path integrals in quantum gravity coupled to matter fields. Okay, and so we need to include all the contributions of not just the Euclidean action of the gravitational field, but also the quantum contributions of the fields. So there's like a one-loop determinant on these each of these manifolds has next to it everywhere we had e to the Euclidean action, there's a quantum fluctuation term on top of that action. And you can kind of imagine that since we're looking at replicas of these, that quantum correction will have to do with the calculation of the matter fields on the replica, and therefore with the entanglement entropy of the matter fields. I'll give a slightly more detailed explanation of this next time when we talk about holographic entanglement entropy. But for now, I'll just tell you the answer is that when you include the quantum corrections, you have several different types of corrections. You have the area, so the leading term is the one we just calculated, just the area. Then there's a S of rho out from the quantum field theory. That is the entanglement entropy of the quantum fields, where out is this region between the black hole horizon and infinity. But there are other types of terms that you get. You get a delta area term. This term is there because the one loop stress tensor of the quantum fields backreacts, changes the area a little bit. So you should think of this as a correction to the area term that comes from the energy of the quantum fields. And there's another type of thing that can enter called the Wald type terms, which I don't really want to say much about, but this has to do with couplings of matter fields to curvature. Like if you have something like phi r in the action, then you can get contributions that come from those type of terms. I think we can view these as contained in the von Neumann term. Yeah. Okay, let me just leave it at that for now for the quantum corrections, and I'll give a only slightly better discussion when we talk about holographic entanglement entropy. But for now, we're done with generalized entropy, and we're moving on to other types of entropy calculations. So let me pause here again for questions.
So this gives you the full expression for generalized entropy, not just the area term.
The replica trick?
Yeah.
Correct.
With one correction.
That's right. That's right. Yeah.
A question.
Yeah.
So this calculation is calculating the fine-grained entropy.
Yeah.
1 minus beta d beta is calculating the thermodynamic coarse-grained entropy. Why are they the same?
Well, you should think of this as calculating the fine-grained entropy of the thermal state, which is a coarse-grained entropy. I mean, it's the von Neumann entropy of the thermal state, but that's the same as the thermal entropy. So it really is, I mean, the coarse-grained entropy is the fine-grained entropy of the thermal state.
Didn't you talk last time about there being an infinite part of the finite entropy of the thermal state?
Yeah.
Entropy was just a
So
finite part.
in this case, that's true when you have a subsystem. Here we were talking about the entropy of the full system. So there's no issue like that. We're talking about the entropy of the full system, so it's literally equal to the coarse-grained thermodynamic entropy.
In this derivation, except for the last step, you didn't have to make use of a particular theory of gravity, right? So only in the very last step.
You mean the step of actually calculating that curvature term?
Yeah.
Yeah, that's right. That's right. So this derivation also will give walled entropy if you consider higher curvature corrections.
So basically that term I should just replace by r plus alpha r squared or something to get higher curvature. But
yeah,
still it's
that's
over
right.
that
That's right.
regular itself.
Correct. Yeah. This is probably the easiest way to derive the walled formula.
Oh, yeah.
Okay, so the next topic is holographic entanglement entropy. And I've purposely gone like very carefully through the replica method of generalized entropy and everything, so that we can see that this is basically the same. It's just a slightly different setup, but it's basically the same object. But it has a very interesting physical interpretation that goes with it, so I'm going to focus on that, and we won't have to do much math. So let me state the formula to begin. So we have, so this is in the context of ADS CFT, although as we'll see, it really goes beyond that. But for now, we're talking about ADS CFT. So we have an asymptotically ADS space-time. Which we can think of as having a conformal boundary where there's Minkowski space that I've drawn here. So time is going up on this picture, and this is a Lorentzian picture. And the holographic entanglement entropy formula is a formula for the von Neumann entropy in the CFT. Well, or the bulk. I mean, they're dual to each other. They have the same quantum states. So you can think of it as the von Neumann entropy of the bulk theory. But it's the von Neumann entropy associated to a subregion on the boundary of the bulk theory. So here's the formula. S of rho A, the von Neumann entropy in the CFT or at the boundary of this theory of quantum gravity, is equal to min A tilde x A tilde S gen of A tilde, where S gen of A tilde, well, let me draw A tilde first. So A tilde is a region in the bulk that ends on the boundary of region A. So it's like a region that extends out. And S gen of A tilde is the usual generalized entropy. It's a quarter of the area of chi, where chi is this surface that I drew, plus S of rho A tilde, which I'll define in a second.
Is chi just the boundary of A tilde? Or did you-
Well, not exactly, because A tilde also has a boundary component, which is A itself. And we do not include that in the generalized entropy. The way to think about that is really when we write the generalized entropy, you only get an area term from pieces where gravity is a fluctuating field. Okay, so like at the boundary of ADS, the metric is actually fixed. There's no fluctuating gravity at the boundary of ADS. So we just don't include that in the definition of generalized entropy for this region A tilde. Okay, so let me say a couple words and then I'll write a couple things more carefully. First of all, this is a formula for the entropy, but it's really much deeper than that. It's a formula. It's really a formula for how holography works. And I'm going to say more about that, but just to preview it, this procedure of extremizing the generalized entropy, what it does is not only spits out for you a formula for the entropy, it spits out for you a region, A tilde. Okay, so to every region on the boundary, there's an associated region in the gravitational theory in the bulk. And you should roughly think that region A tilde in the bulk is dual to region A in the boundary. Only roughly, though, and we're going to have to be careful. We're going to talk about that. Okay, but roughly, this is true. In particular, to say it more carefully, any physics in region A tilde is encoded in the density matrix rho A. That part is a carefully true statement. Okay, so let me write a couple of things. So rho A tilde tilde means the density matrix of the bulk quantum field theory min A tilde next A tilde. So what does this mean? Well, let me say it in words first. So you want to extremize under deformations of the region. And what that always ends up being is it ends up being a minimization in the spatial directions. So like if it should be a minimum under deforming this this way, the S gen should be a minimum. And it ends up always being a maximum in the time directions. Okay, so another way I can say this is that we take a local min under space-like deformations of chi and a local max under time-like deformations of chi. So that's what ext means. Think of this as like, okay, if we're in 2 + 1 dimensions, you just solve the geodesic equation. Because in 2 + 1 dimensions, this thing is just as drawn. Chi is a line, so it's just a geodesic. You just solve the geodesic equation. Okay, min. This extra min out front means that you pick the global minimum. The extremization is a local procedure where you locally extremize, and then the last step is if there are multiple local extrema, you pick the one with minimal entropy. So this is the global minimization.
When you say it's a time-like maximum, you mean if I take the surface A tilde and I start bending it upwards, literally upwards, then the action will decrease.
Well, actually, the calculation of S gen doesn't. It really only cares about chi. You know, I've written it as if it cares about A, but like, if you take this surface and you like put a lump in it like that, that doesn't affect anything. But yes, if I put a lump in chi in the time direction, then S gen should go down because it's a maximum in the time direction. Yeah.
Can you say again what this global that you wrote at the end means?
I mean, so extremization, it's like if, say we're doing geodesics, there might be multiple geodesics that go from here to here. I'm going to give an example, but if there are multiple ones, you should pick the one with the smallest, that gives the smallest answer for the entropy. That's the global minimization.
So the first line, local minimum square information, that's for the X part? And
Yeah.
the global is for the min part?
Yeah, both of these local min and max, that's X'd,
Okay.
and then the min A is global.
Yeah, you said that that X is the same as solving the geodesic equations.
In 2 + 1 dimensions, it is.
It's the generalized entropy, not the proper length, proper time.
Well, in 2 + 1 dimensions, the area just means length in 2 + 1 dimensions.
So the thing that you're extremizing is not S-gen, it's the area?
No, it's S-gen, it's that thing there, but area means
Yes. Okay.
area means proper area of a codimension 2 thing, which in 4 dimensions would be like a 2 surface, but in 3 dimensions is a 1 surface, also known as a geodesic.
But then there's the other term there.
Oh, the other term is the quantum correction term. That also appears in S-gen.
So it's not exactly solving the geodesic equation because of the correction.
True, yes, right. It's classically solving the geodesic equation, but then there are these quantum corrections, which can be important. Okay, a couple other comments. We're still defining the, we haven't quite finished defining the formula. Okay, so the last thing we need to specify is the homology condition. Now, I kind of did this with my picture, but the homology condition says that the boundary of A tilde is A union chi. In other words, you have to pick a region chi, or sorry, a surface chi. This surface has to be deformable to A. And there could be like weird topology and handles and black holes and stuff like that in the space-time. So for example, if I were to put a black hole here, then this would not be deformable and that would not be an allowed choice of chi. Some terminology at the extremum. Chi is called a quantum extremal surface. Or QES. And A tilde, or I need to draw something on my picture. Not just A tilde, but in fact the causal development of A tilde, which we could, I'll say with a D. So the causal diamond associated to A tilde is called the entanglement wedge.
Shouldn't the diamond go out like that
Nope.
if you're going forward in time?
No, by what this diamond means is everything that's determined by taking the physics at time 0 at A tilde and evolving.
I see.
So it's like everything that's fully determined by A tilde.
Got it.
Okay, I think we've almost finished defining the formula. Just okay, I've given you the sort of most general formula first. It didn't happen this way. This has all been discovered in the last 15 years or so, and it's still kind of like settling down, and the terminology is still settling down. But this happened in many steps by many different, this formula happened in many steps by many different people. But the original version was called the Rutakanagi Formula after its authors, Ru and Takanagi. So the Rutakanagi Formula, okay, and well, specifically what the Rutakanagi Formula means is when you, this refers to the situation where it's a static space-time, and we ignore the quantum corrections. Okay, so in this case, the entropy formula reduces to S of rho A is just the min over A tilde of 1/4 the area. So that's a much simpler looking formula. That's the first one that was understood. The next one that was understood is the non-static, but still ignoring the quantum corrections. And this, well, for this one, you just have to put in the extremise step. Okay, and that's often called the HRT formula after its authors. Inclusion of quantum corrections is something that happened in a series of papers by various people who I'm not going to name, but the final version appears in a paper of Engelhardt and Wall. I'm saying this because people are sort of particular about which name you use, and if you write that one and you call it Rutakanagi, a lot of people will shout at you. So.
In the second case, is the Wick rotation or analytic continuation Euclidean well defined?
Not exactly. Not exactly. I mean, no. Or it may have to be complex. Now, it's generally true in quantum field theory that you can make just about any state from a Euclidean path integral by inserting sources. And it's generally, that's generally true in quantum field theory. It's generally assumed to be true in quantum gravity. And it's only under that assumption that any of this has been derived.
So I mean, I was less concerned with the state preparation. It's more that on the gravity side where you would do this kind of a calculation, you know, you go to Euclidean metric or something.
Well, this calculation, as I've described it, doesn't involve any Euclidean whatsoever. The derivation of this formula involves going to Euclidean.
Yeah, that's fine.
Yes, right. But it's only been derived in cases where you have Euclidean path, where you can use Euclidean path nodes.
I see.
I think it's true in general, because of what I said a second ago, that I think it's just true that you can do just about anything in Euclidean. But it's only been derived under that assumption. Okay, that's the formula. Are there any questions about the statement of the formula? Now I'm going to go through some examples. Let's keep the formula up, and I'll erase this one. I'm going to go a bit through the derivation later, but let me just say for now that the way that I just derived the generalized entropy, if you apply it to this problem instead, you get this formula. Okay, it's not quite that easy, like it's hard. It took many years to be able to figure out how to do that, but it's really the same derivation as the one we just saw, where you do these gravitational replicas. Yeah.
Does the rho tilde of A tilde include gravity?
Yeah, that's a bit of a subtle question. Yes, it does, but only in the perturbative sense. Like, it includes gravitons, one-loop gravitons, stuff like that. It does not include the fact that we might Well, as we'll see later, there are non-perturbative gravitational effects, and you should not include those here.
Okay. Is that term small compared to the area term?
Not necessarily. Not necessarily. The recent developments on the page curve, et cetera, involve cases where the quantum term is as important or is as important as the area term. So I'll go through a few examples of increasing intricacy and interestingness. So let's start with the easiest one, which is a 2D CFT and vacuum. If you recall, this is the Cardy-Calabrese calculation that we did in great detail using the replica method in CFT. We're going to draw pictures at time 0. Everything is time independent. So the region we're interested in is a region A on the boundary. And I'm also going to ignore quantum effects. We're just going to calculate the classical term. Well, I don't have to ignore them. They're small. So we're just going to calculate the classical term. That means that all we have to do is solve the G-Disick equation. Well, the G-Disick in hyperbolic space, wasn't this working a minute ago? The G-Disick in hyperbolic space is a semicircle. So A tilde is this region, chi is the semicircle. That's the Rutakanagi surface / HRT surface / quantum extremal surface. Well, the quantum extremal surface differs from this one by an order h bar amount. Okay, so the Rutakanagi formula tells us that we should calculate the von Neumann entropy S of rho A as 1/4 of the length of chi. Sorry, I don't know if I said, this is the radial direction going into ADS, so this is a surface that's anchored on the boundary. Any guesses what that is? Infinity. Okay, because we're in hyperbolic space, and the boundary of hyperbolic space is infinitely far away. But it's supposed to be infinity, because entanglement entropy is infinite in quantum field theory. So it worked, but we could do a bit better. We could do a bit better. So we're going to regulate it. And the way we regulate it is by putting a cutoff some distance epsilon from the boundary. So now we just calculate the length up to that distance epsilon. And what you find is c over 3 log the length of region A over epsilon. That's the regulated length of that G-Disick, where you have this geometric cutoff near the boundary. And in fact, that's exactly the Cardy-Calabrese formula that we derived before. So this is equal to S of rho A in CFT. Check. And it's a bit mysterious, right? In CFT, that epsilon that showed up was a like a lattice spacing, a UV cutoff of the CFT. In gravity, it showed up as a geometric cutoff. But it kind of makes sense. It does make sense, because going near the boundary of the in gravity is like going into the UV. Okay, so putting this geometric cutoff in anti-de Sitter acts as a UV cutoff from the CFT point of view. oh, I probably should have written the formula for C. So C is the central charge. We were doing a gravity calculation. Gravity doesn't manifestly have a central charge, but there's a famous formula that relates them. The central charge of the CFT is 3 times the ADS radius L over 2g Newton. That can be calculated various ways, for example, by looking at the stress tensor 2-point function or lots of other things. Okay, any questions about that one?
But still, cardiac error pressure is more general, right? It is valid for any C, but this I think is valid for only large C. Right?
Agreed. Yeah. However, I think that you could kind of see that it's general. Okay, so what Juven is talking about is this is a holographic theory, right? So we really only reproduce Cardi-Calabrese in some funny limit of like you have a holographic theory. But I think what would happen in this case is you could include arbitrary higher curvature corrections in your gravity theory and arbitrary matter content, and you would still get this formula. And then that would be a very strong hint that it's true even for non-holographic theories. It's not a perfect derivation or anything, but we think of holographic theories as being an expansion at large central charge. And if this formula is true to all orders in that expansion with any kind of matter content, then it would suggest that it's just plain true, and in this case it is just plain true. Okay, I guess I'm going to erase this one so we can get the formula. We good with this one? Yeah.
So in non-static, you're taking the time-like maximum. In the static case, is it that it's no longer a maximum? It becomes
No, no, it's still a maximum. It's just not necessary to think about it because there's a time reflection symmetry. And so if you just sit at time 0, you'll automatically have found the maximum.
But in the static case, then you're looking for a minimum.
A minimum in the space direction. Sorry, this is all, sorry. I should have said in Rutakanagi, we just set time to 0, and then we find a minimum.
Okay.
Thank you. Okay, example number 2. The eternal black hole. Okay, so eternal black hole just means the usual like Schwarzschild type black hole. You didn't make it by collapsing a star or anything. So the eternal black hole is static, so we can set t equals 0 and use Rutakanagi. What does a black hole look like? Well, I'm going to draw it this way, where the big circle is the ADS boundary. Okay, you can in hyperbolic space, you can either take the flat boundary or you can take the circular boundary. This one's a little easier to draw this way. So this is the ADS boundary, and then there's a black hole in the middle. Let's start with region A equals everything. And apply the Rutakanagi formula. Okay, so we have to find a surface chi, which minimizes the area and is homologous to A. And that's the black hole horizon. So let me convince you that that's right. First of all, it's homologous to region A. We can take this chi and pull it out to region A, which is everything at the boundary. Okay, so that's good. It's homologous. Now, it's not totally obvious from looking at this picture that chi is an extremal surface. For that, we should probably go back to the Penrose diagram, or a minimal area extremal. So in the Penrose diagram, region A is just everything on one side of the black hole. It's everything on the right. And chi is the horizon, which is the point in the middle of the Penrose diagram. And so A tilde is everything outside the black hole on the right. And if you remember the picture of like the Einstein-Rosen bridge, chi is a minimal area. So the Einstein-Rosen bridge looks like, which is the spatial geometry going across this thing. It looks like this tube, and chi is this thing in the middle. So it is a minimal area surface sitting at the horizon. So that's the minimal area surface. Now let's calculate the entropy. So therefore, S of rho A is 1/4 the area of the black hole. And yes, that's what we expect for a black hole. When you just calculate the entropy of everything in a thermal state, you should get the black hole entropy. Questions about that one?
Sorry, so the space-time was asymptotically ADS.
Yeah. So this big circle, that's the ADS boundary.
Is that both boundaries or just one?
That's just one of them. That's this point here on the Penrose diagram. There are two like an eternal black hole in ADS has two asymptotic ADS regions. So this is just one of them.
Tom, am I allowed to boost that region A upwards?
Yeah. Okay, so you want to pick a region A at a later time?
Yeah.
Yeah, the eternal black hole has a time-like isometry, so
Oh, it
that'll
doesn't
give the same
matter.
answer.
Yeah.
It'll have the same minimal surface.
Yeah.
Sorry, another.
Yeah. Yeah, go ahead.
So this is saying you're calculating the entropy of A, which is the entire CFT on
Yeah.
the boundary.
Mhm.
So from the perspective of the CFT, even though you're doing the density matrix of everything, it has a non-zero entropy.
Yeah, okay, good, thanks. I should have reminded you, so when you have an eternal black hole, there are two ADS boundaries. So this is dual to two copies of the CFT that are in a thermal field double state. And if we just look at one copy of the CFT, it's in a thermal state. So we expect to get a big entropy for that one copy. Anything else? Example 3, black hole formed from pure state collapse. This one's kind of cheap, but couldn't resist. Okay, so what does this mean? So a black hole formed from collapse doesn't have the other side of the Penrose diagram. It just looks like this. The dashed line is just r equals 0 in polar coordinates. It's nothing fancy, nothing special. The collapsing black hole is like a star or something that collapsed like this. horizon is here. And let's again take region A to be everything. Okay. Now, what does a black hole look like? A collapsed black hole, what does it look like at late times? Well, just looks like this. So you might think that we're going to get area over 4 again. And in fact, if we use the original Rutakanagi formula at fixed time, that's what you would conclude, area over 4. It just looks like a black hole. But this is a time-dependent situation. And you could argue that we can, okay, so that chi would sit here at the horizon. It's really a circle going around the horizon. But if you could deform, well, I claim that in this case, the nothing surface is also an acceptable choice. Okay, so chi equals nothing. So why is that okay here? The nothing surface would not have worked here. Okay, because if you think about the nothing surface, there's the nothing surface, and now you try to like grow it. It gets a little bigger, and now you imagine growing it and growing it. It's not homologous to region A because the black hole's in the way. You won't be able to deform it to region A. But if you do the same trick here, you can take that surface, pull it back to early times before there was a black hole, deform it to the boundary, and then you can successfully deform the nothing surface to region A. And therefore, S of rho A is equal to 0. And we can see that this black hole is secretly pure. I think that argument is a little cheap, but I also think it's correct. I think it's correct. Really, we'd have to go through and make sure you could really, of course, these formulas are not fully derived, so it's not like you've proved it's pure. You have to go back and check that it's really true in this case, but it does seem to be giving the right answer. We do expect black hole evolution to be unitary. We do expect this to be a pure state, and the Rutakanagi formula is giving us the right answer.
Except it's not the Rutakanagi formula.
See, that's what always happens. Okay, let's stop there.